So we have already been using this regularly. However, what happens when the roots have imaginary parts? Anytime you solve a quadratic, sometimes your parabola does not have any real roots. So we've observed situations in our past where, for one, well, you could have two roots, like this and like this, or it could be going downwards. So this has two, what we would call real roots. Another situation is where you only have one real root, right? We're not going to spend much time on the one real root situation because the chances that we have exactly one point where our parabola touches is not very common. And then the third case is where you have no roots, no real roots. And all that means is that you have two imaginary roots, or two complex roots. So let's say that we wanted to solve this quadratic equation here. So we would start off by saying x equals negative b plus or minus the square root of b squared minus 4 times a times c all over 2 times a. And that gives us negative 4 plus or minus the square root of 84. I think that comes out to negative 100. Negative 100 plus 16 is negative 84. Okay, and that's all over 2 times a. Now, you see that we have a square root of a negative. So the one thing that I could do here is continue to break this down and write this as negative 4 plus or minus the square root of negative 1 times positive 84 all over 2. Now, if you take the square root of a multiplication of two things, what we know from algebra is that that is the same thing as taking the square root of negative 1, multiplying it by the square root of 84. This does not work if it's addition or subtraction, it's only if it's multiplication or division. All over 2. Okay, now the square root of negative 1, we know that that's an imaginary number. Because what number times itself gives me negative 1? Well, I could do 1 times 1, which is positive 1, or negative 1 times negative 1, which is still positive 1. So we give this guy a name. We call this I. And I just stands for the square root of negative 1. So that's just the symbol we use in place of that. So here we're going to have negative 4 plus or minus, now the square root of 84 I could approximate, but I'm just going to leave it as the square root of 84, multiplied by I all over 2. So because I have a plus or minus, I'll divide this by 2, I'll divide this by 2, and now I see that my root to this equation is I have negative 2 plus or minus the square root of 84 over 2 times I. All right, so we have two pieces to this puzzle. First of all, we see that anytime we have complex roots, it's not super hard to see that we're going to have both of our roots are going to be of the form a plus or minus bi. So like here our a is, I'll use a different color. Here our a is negative 2, and our b is square root of 84 over 2. So these are going to become important. A is called the real part, okay, and they come in complex conjugates, meaning that you'll have a plus bi and you'll have a minus bi, and that's always true if you're going to have complex roots. So a itself, negative 2, is called the real part because it's the real part of this complex number. A complex number could have a real part, an imaginary part, or both. And b is called the imaginary part. Now, people want to say it's square root of 84 over 2i is the imaginary part, but no, we're referring to just the coefficient, square root of 84 over 2. So this is equal to, that's equal to a, that's a right there, and this number right here is b. Together, a plus or minus bi is called a complex number. Now, we'll prove this at the end of the lesson, but for all intents and purposes, just to be able to demonstrate this, let's go ahead and state the theorem first. So what happens if you have complex roots? Well, consider our differential equation. This is the same thing as what we were dealing with up here. up at the top, except now suppose the roots of the equation r squared plus cr plus d equals 0 are complex, such that the value of r that you find is a plus or minus bi. Then the general solution is as follows. Y equals k1 e to the at, so notice that a is, whatever a is, that's going to go here, and it's going to go here. k1 e to the at sine of bt. So b is there, and so b goes there, and b goes there, and that's going to form your general solution. So it's kind of fun to see that if you have complex roots, you have a mixture of exponential and sinusoidal functions. Let's go ahead and put this to play and see how this works. So here we have y double prime plus 4y prime plus 25y equals 0. So again, our guess, just to see how this guess evolves, would be y equals e to the rt, so y prime equals r e to the rt, and y double prime equals r squared e to the rt. And when we plug these components in, we get r squared e to the rt plus 4r e to the rt plus 25 e to the rt equals 0. And again, you see we factor out e to the rt. This part's very consistent regardless of whether or not you're going to have real or complex roots. We just don't quite know yet. Now we find the roots of this guy. I'm going to go ahead and jump to Wolfram Alpha and do this, since I don't really feel like computing it. Now, as mentioned, using Wolfram Alpha, you can just enter it in as you see here, and it comes up with two complex roots. Now this is the same equation that we were solving up here. We were just using x. We didn't quite get the same answer, which is sort of odd. They came up with -2 plus or minus the square root of 21 times I, but we came up with -2 plus or minus the square root of 84 over 2 times I. And it turns out that you can actually reduce this further. -2 plus or minus, you can actually break up 84 into two factors, the square root of 4 times the square root of 21. And that's over 2, and that's over 2 times I. Square root of 4 is 2. 2 over 2 cancels, and so you see we get, not -2, this is not -2 over 2, just -2. And so you see we get -2 plus or minus the square root of 21 times I. So same thing Wolfram Alpha gives us. Wolfram Alpha reduces it for us quite nicely. All right, so our value of r is -2 plus or minus the square root of 21 times I. So we want to identify our a and our b. Here our a is -2. Our b is square root of 21. Notice that b is always going to be the unsigned value, so there's always going to be a plus or minus here, but you're just taking the positive square root of 21. And so our general solution is going to be y equals k1 e to the at sine of bt plus k2 e to the at cosine of bt. And once again, now we can satisfy our initial conditions. Here's where things get a little messy, just because taking the derivative of this requires using the product rule. So this is the position, and let me just go ahead and set that up. We know that the initial position is 1, so 1 equals. Now here's the nice part. k1 e to the 0, that's just going to be k1, but sine of 0 is 0, so this will be 0 plus e to the 0 is 1, cosine of 0 is 1, so this will just be k1 equals 1. Perfect. So that solves for our k1 value. Now to get velocity, we have to take the derivative of this function, and that's where I just said it gets a little bit messy. So by the product rule, it's f prime g plus fg prime. So k1, the derivative of e to the -2t is -2 e to the -2t. Second function untouched. Plus the first function times the derivative of the second, which is going to be the square root of 21 cosine of the square root of 21t. And then we have to take the derivative of this whole second term, which will be very similar, plus -2 k2 e to the -2t cosine square root of 21t. That's the derivative of e to the negative 2t times cosine untouched, plus the first untouched times the derivative of the second, which will give us a negative, since the derivative of cosine is negative sine, and it'll be negative square root of 21, k2 e to the negative 2t sine of square root of 21t. So it gets a little bit messy because of that two product rules in there. But now we can substitute in our initial velocity, which is 0. Well, this should be y prime. So 0 equals, and if we look at these terms term by term, the signs are going to be 0 because you plug in 0, sine of 0, 0. And so then we can, so that'll be 0, this will be 0. This will give us e to the 0 times cosine of 0, that's 1. So that will leave us with square root of 21 k1. And this term here, e to the 0 is 1, cosine of 0 is 1, minus 2 k2. Now I could dump this into Wolfram Alpha, but this is a really quick solve. If I just plug in k1 equals 1, I'll have 0 equals square root of 21 times 1 minus 2 k2, and subtracting that over, dividing by 2 gives me k2 equals square root of 21 over 2. So now my final solution is just going to be a matter of replacing k1 and k2 in my original solution. So I'm going to go ahead and just lasso this guy here and replace k1 and k2. All right, so k1 we just said was equal to 1. And k2 is equal to the square root of 21 over 2. You can approximate that if you want. I'm just going to leave it as that since I have square root of 21 in here. So let's go ahead and graph this and see what happens. Now, we do have sine and cosine in here, but the other thing that we should note is that this coefficient, that the coefficient of a sine or cosine function controls the amplitude. So these guys here are going to be related to the amplitude. Now, the thing is, amplitude doesn't always have to be constant. So as t gets larger and larger, the amplitude is going to get smaller and smaller at an exponential rate. So what we're probably going to see is we're going to see some oscillations that are going to slowly or quickly fizzle out over time. Now here we have that graph. You can see that our initial position, I did catch a little mistake here before we do that. Here, this should have been k2. Maybe you caught that already. It should be k2 is equal to 1. k2. Apologies for that. And then here, this means that this statement is still going to be true, but we should replace k2 with 1 and leave this unbeknownst. So let's go ahead and resolve this. So this should be 0 equals square root of 21 k1 minus 2k2, which is just negative 2. Add that to the other side, divide by square root of 21. We get 2 over the square root of 21. So it's just going to invert our fraction here. 2 over the square root of 21. All right, change that back here. 2 over square root 21. And now that looks a little better. And I think we'll get this eventually. So k1 should actually be 2 over the square root of 21, and k2 is 1. So, and the reason I knew that is because my initial condition was kind of off. So when you do notice your initial condition is off, that usually is a good indicator that something is not quite right. So we'll go ahead and put that back over here. There's our 2 over the square root of 21. So there's our initial position. We have an initial decrease in the rate of change, and watch what happens to that spring mass over time. That green thing starts at rest and oscillates a little bit and then quickly returns back to rest. Now we can slow that down just a little bit more, and so you can see it in all its glory. A little bit of so we start off with the spring mass system is stretched 1 meter from its displacement. returns to rest, compression, a little bit of a stretch, returns to rest, a little bit of a compression, returns to rest again. We can make this difference seem as large as we want. If we zoom in on it, you can see that it's still continuing to oscillate forever and ever and ever, but it happens really quickly. Now, the reason this is happening so fast is because our decay rate is 200%. But if we made this, for instance, negative 0.2, let's just say hypothetically that's what our A value was, you still get that exponential decay in the peaks. You can see that the peaks are kind of getting smaller by an exponential factor. And if that decay rate is a lot smaller in the spring mass system, usually it's caused because of the damping. Your damping isn't that strong, so the mass is able to oscillate more. But in our case, our A value is a lot larger, and as a result, we get these very fast decays. So that gives us a good sense of how to solve systems with complex roots. We will derive the why this works at the end of the video in case you're intuitively curious how that works. It is a very beautiful mathematical process.